In this presentation, we are going to discuss about the virtual memory. The contents are background about the virtual memory and the demand paging. The objective was define virtual memory and describe its benefits. Then illustrate how pages are loaded into memory using demand paging. Apply the first in first out and optimal and LRU page replacement algorithms. In the background, the code needed to be in the memory to execute, but entire program rarely used. So the error code, unusual routines, large data structures, like that. So the entire program code not needed at the same time. So the consider ability to execute partially loaded program. So the program no longer constrained by limits of physical memory. Each program takes less memory while running. More programs run at the same time. Increased CPU utilizations and throughput with no increase in response time or turnaround time. So less IO needed to load or swap program into memory. So each user program run faster. And this what is in virtual memory? So it is in separations of user logical memory from physical memory. Only part of program needed to be in memory for execution. Logical address space can therefore be much larger than physical address space. So allows address space to be shared by several processes. Allows for more efficient process creations. More program running concurrently. So less IO needed to load or swap process. So in this virtual address space that is needed. Okay. So the logical view of how process is stored in memory usually start at address 0, contiguous addresses until end of the space. When the physical memory organized in page frames also, then memory management unit must map logical to physical. So virtual memory can be implemented in demand paging and demand segmentation. So the virtual memory that is larger than the physical memory that can be explained here. The virtual memory space is more. So it is used for the reduce the execution time. Okay. So the physical data are captured from the main memory for the processing. So in that time the frequently used data are mapped from the backup storage to the virtual memory for easy to access. So the virtual address space usually designed logical address space for stack to start at max logical address and go down while heap grows up. So maximize address space use and use address space between the two is a whole. So no physical memory needed until heap or stack grows to a given news page. Enable sparse address space with holes left for growth, dynamically linked libraries, etc. System libraries shared over the mapping into virtual address space. Shared memory by mapping pages read write into virtual address space. So shared library using virtual memory. So the shared libraries, everything stored into the memory that is occupied in the whole. So these pages are belongs to the shared page. So that is moved to the virtual memory. The demand paging cloud bring entire process into memory at load time. Bring a page into memory only when it is needed. So less input needed, no unnecessary input output. So less memory needed. So faster response, more users. So in that time The similar to paging system with swapping. Here the page is needed, so the reference to it. Invalid reference, it is an abort. So not in memory, bring to memory. So lazy swapper. So in that method, never swaps a page into memory unless page will be needed. Swapper that deals with the page as a pager. So in the demand paging, could bring entire process into memory at load time and bring a page into memory only when it is needed. So the basic concepts is, with swapping, page guesses which pages will be used before swapping out again. Instead, pager brings in only those pages into memory. How to determine that set of pages? Need new memory unit functionality to implement demand paging. If the page needed are already memory resident, no difference from non-demand paging. If the page needed and not memory resident, need to detect and load the page into memory from the storage. So the valid and invalid bits are used for this reference. So with each page table entry, a valid invalid bit is associated because for the referring of the data information from the memory. Initially, valid invalid bit is set to 1 on all entries. That is a value of I. Okay. So examples of page table snapshot where the contents, the pages are valid or invalid. Okay, valid or invalid bit is set to I in all entries during the memory processing unit address translations. If valid invalid bit in the page table entries is I, the page is fault. Page table when some pages are not in main memory. So in this logical memory, consider A to H. So from this, the page table is also has the 7 pages. Then the physical memory has ACF. Okay, so here some pages are not available in the main memory because it is not frequently used. So it is in the backing storage. So in that time the virtual memory is needed to swap that process. So it is in page demanding. 2 steps in handling page fault. If there is a reference to a page, first reference to that page will trap to operating system. That is in page fault. Operating systems looks at another table to decide invalid reference, that is to be abort, just not in memory. So find the free frame, swap the page into the frame via scheduled disk operations. Resets the table to indicate the page now in the memory switch validations bit is equal to 1. Restart the instructions that cause the page fault. If the page fault occurs, the needed page is referred from the shared memory, then it is copied to the main memory. Okay, so now it is a valid bits are set to V, so we can stop the executions. The performance of the demand paging. So in the stages in the demand paging, sometimes it trapped to the operating systems, it is save the use the registers and the process state. Then determine that the interrupt was a page fault. Then check that the page's reference was legal and determined the locations of the page on the disk. Issues a read from the disk to a free frame. Wait in a queue for this device until the read request is serviced. Wait for the device is a current latency time. Begin the transfer of the page to a free frame. So this is the process going to be done. So while waiting, allocate allocate the CPU to some other user. So receive an interrupt from the disk IO systems and save the registers and process states for the user. Determine that the interrupt was from the disk. Correct the page table and other tables to show. Correct the page table and other tables to show the page is now in memory. Wait for the CPU to be allocated for this process again. Then restore the user registers process states and new page table and then resume the interrupted instruction. So need for the page replacement. Need for page replacement here. We want to load the yum process in the user 1. So that is refer from the shared memory, but because not available in the physical memory, so refer that, then it is restored into the physical memory. Thank you.